Math 1314 IC1, Spring 2022, Tyler Junior College. Homework 9.3/9.4, Logarithms and their properties. Video 5, Evaluating Logarithms. Now, in the previous video, we did evaluate some logarithms as we introduced two special logs, log with no base, which means log base 10, and natural log, ln, which means log base e. But in general, a log will have a base. Well, a log will always have a base, and most of the time it's written. Log and ln are the exceptions. But regardless, many logarithms can be evaluated without really relying on a calculator as long as you understand the question. So in this video, what we're going to do is actually go into the homework and look at some of the specific questions and give you an idea on how to attack them. Now, this is homework 9.3/9.4. And I've gone to question 9, and the question 9 in my version, because in your version the numbers may be a little bit different, says log base 2 of 32. And I want to point out that notice that they did not put parentheses around the 32. That's okay, because the argument is a single term, 32. I like putting parentheses around my argument because a logarithmic function is first and foremost a function like f of x. And when you type that, or when you write that, you put parentheses around the x, the argument of that function. So I'm going to write them with parentheses around the arguments, although in the homework, they will often not do that if the arguments are single terms. All right, let's see if we can evaluate log base 2 of 32 without a calculator. All right, log base 2 of 32. We want to know what this equals. We can put a question mark, an X, a box. I'm going to put a box. I told you I'm going to sound like a broken record because I'm going to say this so many times you're going to get sick of hearing it. What is the answer to a logarithm? The answer to a logarithm is the power that turns the base into the argument. Now, this is the generic answer to what is a logarithm. But we can make it specific for each problem. So we'll say the answer to this logarithm is the power that turns the base. But what is the base in this problem? 2 into the argument. And what is the argument in this problem? 32. You don't have to know what the answer to a log is, but at least not initially. But you do have to know what the answer to a log does. In this case, whatever this answer is the power that will turn 2 into 32. And then the hunt begins. Now, how can you find the power that turns 2 into 32? Well, there's a couple of ways to do it. One is to just keep multiplying 2's until you found the correct number and hope you didn't miscount. Or you can take the 32 and break it down. What do I mean by break it down? Well, break it down until it's nothing but 2's. Now, you can start by breaking off 2's, but my advice is to use the largest numbers possible, largest pair of numbers possible. For example, I can rewrite 32 as 4 times 8. Now, neither one of those are 2's, but if we break down the 4 into 2 times 2, there's a pair of 2's. I'm going to circle them. That's what we're looking for. 8 is 2 times 4. There's another 2. And then 4 I can break down even further into 2 times 2. And notice I circled every time I got to a 2. It took 5 2's to make 32. In other words, 2 to the 5th power is 32, which means log base 2 of 32 is 5. No calculator needed. I just had to know what the answer did and then find the power that works. Let's take a look at another one. Go back to the homework. I don't know how many of these are going to do until I feel like I've discussed it enough. How about this one, log base 3 of 1? What question is this problem asking? What question is log base 3 of 1 asking? Log base 3 of 1 is equal to something. What question does this problem ask? Well, it asks the same question as before. Or rather, it says the same thing. The answer to this logarithm is a power that turns one thing into another. You might hear my dogs barking in the background. I may have to go tell them to stop that. The answer to this log is the power that turns the base, which is 3, into the argument, which is 1. Okay, well, what power turns 3 into 1? Now, I can't do this like the previous one because I can't break down the 1 to see how many 3s it's made up of. It's not made up of any. Oh, wait a minute. Anything to the 0 power is 1. Anything to the 0 power is 1. And if you think about it, this answer was destined to be 0 regardless of the base. This was equal to 0 because the argument was 1. So we can do what's called a generalization or a property where we capture the essence of how this problem works that relies on something specific about the problem, but everything else is generic. For example, the 3 was not really that important in this problem. If that 3 had been an 8, it still would have been 0. What made this problem work? Not the 3, the 1. So in general, we can say the following. If we have any log, any base except 0, and the argument is 1, then that's going to equal 0 every single time, as long as the base is not 0. Actually, by definition of a logarithm, the base has to be positive, but the base is not equal to 1. All right, let's take a look at another. I think the dogs outside are quiet now. Let's scroll through these and see what type of issues show up. 11. Ooh, no base is written, which means, well, it's log, so it's base 10. What power turns 10 to 100,000? Hint, count the zeros. Log base 2 of 1 over 8. Okay, I think this one merits working out. Or do you know it already? Do you know what log base 2 of 1/8 is? Log base 2 of 1/8. Now, if you can look at it and think the answer, that is awesome. But you still should know what the answer is supposed to do. Whatever this answer is, this answer, the answer to this log is the power that turns what into what? Turns the base 2 into the argument, which is 1/8. So I need to know what power do I put on 2 to get an answer of 1/8. Well, we can reverse engineer the 1/8 by reverse engineering the 8. Now, if you didn't know how many 2's you multiplied to get 8, you could break it down. 8 is 2 times 4, there's a 2. 4 is 2 times 2, there's the rest of them. 8 is made up of 3 2's, it's 2 to the 3rd power. So we could rewrite 1 over 8 as 1 over 2 to the 3rd. We have an exponent rule that says this is equal to 2 to the -3 power. The power that turns 2 into 1 over 8 is -3. Which means the answer to this logarithm is -3. Let's find a really good one, shall we? We did like this one like this in the previous video. I'm not going to write it down on the whiteboard, but knowing that natural log has a base of e, and the argument of this logarithm is e to the 8th, e to the 8th. The question is, what power do you put it on? What power turns e into e to the 8th power? What power turns e into e to the 8th power? 8 is the power that turns e into e to the 8th power. Oh yeah. Let's find something that we haven't done yet. Ooh, what about this one? Natural log of 1 over e to the 4th. Do you think you know what it is? Let's take it to the whiteboard. Sometimes when you're doing a logarithm problem, like natural log of 1 over e to the 4th, it's useful if you can write the argument as a power of the base. Now, the natural log is an implied base e. So can we write 1 over e to the 4th as e to some power? In other words, what power would we put here to get this? Well, what types of powers make reciprocals? Negative powers. The power that would turn e into 1 over e to the 4th is -4. So if we wanted to, we could rewrite the problem as natural log of e to the -4. Because in my opinion, in fact, this will be a property that we summarize in the next video, the part highlighted answers itself. Because the question this asks what power turns e into e to the -4 power? Well, -4 turns e into e to the -4 power. So if it's plausible to write the argument, in fact, this is worth writing, and I'm going to write it in black. If you can write the argument of the logarithm, so the part in parentheses, as a power of the base, in other words, the subscripted number, then the answer to the logarithm is that power. So what we just did here, we wrote the argument 1 over e to the 4th as a power of e because e was the base. It was e to the -4 power. And now the question is, what power do you put on e to turn it into e to the -4 power? Now, this is something we could actually write as a property. If you can write, let's make it as generic as possible. How would we write a generic base? How about with a b? If you can write the argument of the logarithm as a power of the base. So if the argument is b to some power, we'll put an n there. Then the answer to the logarithm is that power, because the question is, what power would I put on this to turn it into that? Well, isn't the power that would do it that one? It is. The power that turns b into the b to the nth power is n. This is going to be a property that is summarized in the next video. There's one more type of problem I want to try to find. Let's see if I can find it. There it is. Log base 9 of the 6th root of 9. Let me see if there's any other issues, because this may be our last example. That one kind of carries the same issue. We actually just did that one, if you think about it. This one's easier than it looks because the argument is 1. It's the same problem, just different base. Anytime the argument is 1, the log is equal to 0. All right, that crosses into something different. Now, where was that problem? It was log base 9 of the 6th root of 9. This one is so easy if you have the correct exponent rule at your disposal. Log base 9 of the 6th root of 9. Now, quit worrying about how to figure out what the 6th root of 9 is. Worry about what the answer to this is supposed to do. Well, I'm not going to type the words because the argument is the 6th root of 9. I am, however, going to write what the answer is supposed to do. The answer to a log, which currently is a rectangle, is a power. It's supposed to be in red. It's a power that turns the base, which is 9, into the argument, which is the 6th root of 9. So we really got to figure out what makes this work. Well, this goes back to what it means to take a root of a power. Recall that the exponent rule that we had before was the wife root of b to the x power is equal to b to the x over y power. And remember, the trick for remembering that was the top half of this radical kind of looks like a division problem. It looks like x divided by y, which is just another way of writing x over y. So if we're going to change a radical into a power, a root into a power, we need to be able to see the index. The index is the part right there in the radical, in this case, the 6, because the index becomes the denominator over here. But we also need to be able to see a power on the x, on the base, excuse me. There is no power on this 9, except there is. What power is there when you can't see it? First power. So how can we rewrite the 6th root of 9 to the first power? Well, think about the division problem right here. 1 divided by 6. Well, 1 divided by 6 is the same as 1 over 6. Supposed to be drawing here. So the power that turns 9 into the 6th root of 9 is the 1/6 power. And so the answer to our logarithm is 1/6. I want to end this video with one quick comment. The exponent rule in play here to answer the question, what power does this, is the y root of b to the x is equal to b to the x over y, which is true. But more often than not, there won't be an explicit power on the base. This 1 is only there because I needed a power there, and the only power you can drop in, but that's not there, is a 1. So would it be beneficial to say, well, what if we have the y root of some base that doesn't have a power on it? Well, the implied power is 1, so this is the same as b to the 1 over y power. It might be nice to have both of those exponent rules in your arsenal. The truth is, only the top one is necessary, because the bottom one is just the top one if you pretend x equals 1. But sometimes it's nice to have the shorter version, because more often than not, you'll see a root with an index, but not a power, like the 6th root of 9.